Good morning, class. I hope everyone had a wonderful night of sleep. Today, we have an exciting lesson ahead, so let's get started. Now, please open your textbooks to page 23. We'll be discussing the importance of active reading strategies. Remember, taking notes and highlighting key points will help you absorb the material better. I see some of you have brought your coffee cups with you today. Just a quick reminder, while caffeine can provide a temporary boost, it's important to maintain a balanced study routine. Take short breaks to stretch your legs and recharge your focus. Now, let's move on to the mathematics problems on page 30. Don't be afraid to ask questions if you're unsure about any step. Remember, practice is the key to mastering any subject. Our coffee break is coming up in about 15 minutes. During that time, feel free to enjoy your coffee cups and have a quick snack. But also, take a moment to review what we've covered so far. Alright, class. Let's continue with our lesson and explore the historical events that led to the Industrial Revolution. Understanding the past helps us make sense of the present and prepare for the future. I'm glad to see your enthusiasm for learning today. Keep up the great work, and don't forget to take care of yourselves both mentally and physically. Your education journey is a marathon, not a sprint. That's all for today. I'll see you in our next class. Have a wonderful day and don't forget to grab your coffee cups as you leave. Good morning, class. Good morning, class. I hope you all had a wonderful night's sleep. Today, we're going to dive into an exciting new topic. But before we begin, let's take a short break to stretch our legs and grab a quick sip of coffee or your favorite beverage. Now, back to our lesson. I want you all to pay close attention as this material will be important for the upcoming assignment. Remember, participation is key in this class, so don't hesitate to ask questions if you're confused. Learning is a journey, and we're all in this together. Alright, let's continue with the next section. But before that, take a quick moment to take a sip from your coffee cup and let's proceed. Great job today, everyone! Don't forget to review the material before our upcoming quiz. Have a productive day, and I'll see you all in our next engaging class. Good morning, class. Greetings, knowledge seekers. Our understanding deepens as we explore the critical role of pressure control in calorimetry. Achieving precise measurements of delta H hinges on this control. Reactions taking place in solutions provide us with the luxury of managing pressure with relative ease. However, in our trusty coffee cup calorimeter, since it's not sealed, we make an assumption of constant pressure due to the open nature of the system. This assumption helps us understand the basics of heat exchange. Yet, for those pursuing ultimate accuracy, high-end calorimeters with sealed systems are the tool of choice. They allow us to meticulously manage pressure conditions and provide us with unparalleled precision. As we continue, we'll appreciate the balance between simplicity and precision in calorimetry. Greetings. Welcome, class, to our vocabulary lesson for today. Today, we'll be exploring the word coffee cup. Let's break it down and understand its components. The word coffee refers to that aromatic, energizing beverage many of us enjoy to kickstart our mornings. It's made from roasted coffee beans and often accompanied by a pleasant aroma that wafts through the air. Now, let's turn our attention to the second part of the word, cup. A cup is a small, cylindrical container used for holding liquids, like coffee. It usually has a handle for a comfortable grip and comes in various sizes and materials. So, when we combine coffee and cup together, we get coffee cup. It refers to the vessel specifically designed to hold and enjoy that delicious coffee we mentioned earlier. Now, let's take a moment for a little brain break. Take a deep breath in, and exhale. Great. Now, let's continue. In conclusion, a coffee cup is more than just a container. It's a companion to those quiet moments of contemplation and the perfect partner for our favorite brew. Thank you for joining today's vocabulary exploration. Remember, words are fascinating windows into the world around us. Until next time, keep learning and savoring those coffee cup moments. Class dismissed. Welcome, class. Welcome back, curious minds. Now, let's focus on the heart of our discussion. Enthalpy changes in atmospheric pressure. Enthalpy change is essentially the heat that's either released or absorbed during a chemical reaction. What's intriguing is that our planet's atmosphere plays a key role in maintaining the constant pressure within open systems, like our beloved coffee cup calorimeter. The stability of the calorimeter's setup depends on this atmospheric pressure. As we journey further, we'll uncover the connection between pressure and enthalpy changes, leading us to a deeper comprehension of the energy dynamics involved in chemical processes. So, stay with me as we unravel the mysteries of enthalpy and atmospheric influence. Welcome back. Hello, inquisitive scholars. Let's elevate our understanding to precision levels as we explore advanced calorimetry techniques. Precision calorimeters are designed for those seeking unparalleled accuracy in heat measurements. By employing sealed systems, these instruments provide meticulous control over pressure conditions, ensuring minimal external influence. These setups are the pinnacle of calorimetry, used in scientific research to unlock the mysteries of complex reactions and energy changes. So, as we wrap up our journey today, remember that precision and attention to detail are at the forefront of scientific exploration. Keep your passion for knowledge burning bright, and let's continue our quest for understanding the intricacies of energy and chemical processes. Hello, students. Today, we're delving into a fascinating concept known as coffee cup calorimetry and its connection to heat transfer. Imagine you have two aqueous solutions, each containing a reactant. When these solutions are mixed, a reaction takes place. What's intriguing here is that there's no physical boundary separating the system from the surroundings. The reactants and products of the reaction form the system, while the water in which they are dissolved becomes part of the surroundings. And let's not forget, the coffee cup calorimeter itself is also part of these surroundings. Now, let's imagine the calorimeter is perfectly insulated, allowing us to focus on the heat exchange between the system and the surroundings. Keep in mind that any heat released or absorbed by the reaction will cause a temperature change in the water. This change in temperature is a direct result of heat being transferred from the reaction to the water, in exothermic processes, or from the water to the reaction, in endothermic processes. In simpler terms, by observing the temperature of the solution, we're actually witnessing the movement of heat between the system, that's the reactants and products in the solution, and the surroundings, the water that makes up most of the solution. Now, let's explore this concept further. Hello, student. Welcome back, students. Today, we're peeling back the layers of insulated calorimetry and understanding temperature changes during reactions. The beauty of an insulated calorimeter lies in its ability to focus solely on heat exchange. As reactions occur, they release or absorb heat. This energy transfer is what leads to temperature changes. When an exothermic reaction takes place, heat is released, causing the solution's temperature to rise. Picture it like this. The reaction is like a cozy fireplace, warming up the surroundings. On the other hand, in an endothermic reaction, heat is absorbed from the surroundings, which causes the solution's temperature to drop. Think of this like an icy drink cooling down your hand on a hot day. So, remember, the change in temperature gives us a direct insight into the type of heat exchange occurring between the system and the surroundings. Now, let's move on to explore some real-life examples. Welcome back, students. Great to have you with us, students. Today, we're diving into real-life examples where calorimetry plays a significant role. One classic example is combustion reactions, which are typically exothermic. Think of burning wood in a fireplace. The heat released warms the surroundings, and we can measure this temperature change using calorimetry. On the flip side, let's explore the dissolution of salts, which often involves endothermic reactions. Dissolving certain salts in water requires energy input, and this draws heat from the surroundings, causing a drop in temperature. Now, have you ever wondered how cooking reactions relate to calorimetry? When you're cooking, certain reactions release heat, causing the temperature of the dish to rise. This culinary magic can also be understood through calorimetry. So, whether it's warming up by the fire, watching salts dissolve, or creating a delicious meal, calorimetry helps us understand the underlying heat transfer. Let's continue our journey into the world of energy exchange. Great to have you with us. Welcome back. my curious learners. Today, we're delving into a fundamental principle: the law of conservation of energy. Energy cannot be created or destroyed, it merely changes forms. This law plays a significant role in calorimetry. As we've discussed, the heat exchange during reactions leads to temperature changes in the surroundings. This connection between heat and temperature change is crucial. By precisely measuring these temperature changes, we can quantitatively analyze the energy exchange during a reaction. This technique finds applications in fields like chemistry, physics, and even biology. It allows us to delve deep into the heart of chemical processes, from understanding fuel combustion to exploring metabolic reactions in living organisms. So, remember, as we study calorimetry, we're not just learning about heat transfer, but also uncovering the intricate dance of energy conservation. Let's continue this exploration into the captivating world of calorimetry and its implications. Welcome back. Alright class, let's discuss the progress we've made in this project. So far, we have gained a deeper understanding of the subject matter. Our research has led us to some valuable insights. And I must say, the effort you all have put in is truly commendable. We've gained not only knowledge but also teamwork skills throughout this journey. Keep up the great work, everyone. Alright class. Let's take a moment to discuss the concept of being lost. You see, when we use the word lost, it often carries a sense of uncertainty and confusion. It's not just a simple word, it's a reflection of a state of disorientation. When someone is lost, they might feel like they're wandering in an unfamiliar territory, both physically and mentally. It's important to guide our students towards finding their way and helping them overcome that feeling of being lost. Remember, as educators, we have the power to provide direction and create a supportive environment for those who might feel lost. So, let's embark on this journey together and make sure no one is left feeling lost in their learning adventure. Let's take a moment to Hello, dear students. Now, let's delve into the captivating realm of exothermic and endothermic reactions. These reactions teach us about the fascinating interplay between heat and the substances involved. First, let's talk about exothermic reactions. In an exothermic reaction, heat is lost by the reaction itself and gained by the water in the solution. This energy transfer causes the temperature of the solution to rise. On the other hand, an endothermic reaction showcases the opposite behavior. Here, heat is gained by the reaction and lost by the water in the solution, causing the temperature of the solution to decrease. The relationship between heat absorbed or released by the reaction, Crickson, and the heat gained or lost by the solution, Qsoln, is beautifully encapsulated by the equation Qsoln equals Crickson. This equation tells us that these two quantities are equal in magnitude but have opposite signs. Calculating Qsoln becomes a breeze when we know the mass of the solution, its specific heat, and the temperature change. For diluted aqueous solutions, we typically assume that the specific heat of the solution is equivalent to that of water, which is approximately 4.18 J per gram K. Now, let's move on to the next exciting chapter in our journey. Hello, dear students. Fantastic to have you here, students. Now, let's uncover the intriguing link between temperature change and the type of reaction taking place. By observing the direction of temperature change, we can deduce whether the reaction is exothermic or endothermic. When we notice a positive temperature change, increment T is greater than 0. It's a clear indicator of an exothermic reaction. In these reactions, heat is released by the reaction itself and is gained by the solution, leading to a rise in temperature. On the flip side, when we witness a negative temperature change, increment T is less than 0. It signifies an endothermic reaction. Such reactions absorb heat from the surroundings, leading to a decrease in temperature. The magnitude of the temperature change also speaks volumes about the energy exchange involved. Exothermic reactions often display a more substantial increase in temperature, while endothermic reactions tend to exhibit a more significant temperature decrease. Keep these correlations in mind as we journey deeper into the world of energy transformations and their remarkable effects. Fantastic to have you here, students. Now, let's uncover the intriguing link between temperature change and the type of reaction taking place. By observing the direction of temperature change, we can deduce whether the reaction is exothermic or endothermic. When we notice a positive temperature change, increment T greater than 0, it's a clear indicator of an exothermic reaction. In these reactions, heat is released by the reaction itself and is gained by the solution, leading to a rise in temperature. On the flip side, when we witness a negative temperature change, increment T less than 0, it signifies an endothermic reaction. Such reactions absorb heat from the surroundings, leading to a decrease in temperature. The magnitude of the temperature change also speaks volumes about the energy exchange involved. Exothermic reactions often display a more substantial increase in temperature, while endothermic reactions tend to exhibit a more significant temperature decrease. Keep these correlations in mind as we journey deeper into the world of energy transformations and their remarkable effects. Fantastic to have you. Hello, students. Today, we're delving into a fascinating technique known as bomb calorimetry, which plays a pivotal role in understanding combustion reactions. Imagine you want to study a combustion reaction in detail. Enter the bomb calorimeter, a sophisticated apparatus designed just for this purpose. In this setup, the compound to be studied is placed within a sealed vessel, aptly named the bomb, which is insulated and capable of withstanding high pressures. The bomb comes with an inlet valve for introducing oxygen and electrical leads for initiating the reaction. Once our sample is safely inside the bomb, we seal it and pressurize it with oxygen. Now, here's where the magic happens. We place the bomb inside the calorimeter and add a precisely measured amount of water. To kickstart the combustion reaction, we pass an electrical current through a fine wire that's in contact with the sample. As the wire heats up, the sample ignites, and voila, combustion. The heat released during this process is absorbed by the water and the various components of the calorimeter, which together form the surroundings. This absorption causes the temperature of the water to rise. And here's the real kicker: we measure this change in water temperature with exceptional precision. This method grants us insight into the energy released by combustion reactions. Now, let's move on to more exciting concepts. Hello, students. Today, we're delving into a fascinating technique known as bomb calorimetry, which plays a pivotal role in understanding combustion reactions. Imagine you want to study a combustion reaction in detail. Enter the bomb calorimeter, a sophisticated apparatus designed just for this purpose. In this setup, the compound to be studied is placed within a sealed vessel, aptly named the bomb, which is insulated and capable of withstanding high pressures. The bomb comes with an inlet valve for introducing oxygen and electrical leads for initiating the reaction. Once our sample is safely inside the bomb, we seal it and pressurize it with oxygen. Now, here's where the magic happens. We place the bomb inside the calorimeter and add a precisely measured amount of water. To kickstart the combustion reaction, we pass an electrical current through a fine wire that's in contact with the sample. As the wire heats up, the sample ignites, and voila, combustion. The heat released during this process is absorbed by the water and the various components of the calorimeter, which together form the surroundings. This absorption causes the temperature of the water to rise. And here's the real kicker: we measure this change in water temperature with exceptional precision. This method grants us insight into the energy released by combustion reactions. Now, let's move on to more exciting concepts. Hello, students. Welcome back, students. In today's lesson, we're delving into a concept called the heat of combustion and the fascinating world of calorimetry. But first, let's establish something crucial. To calculate the heat of combustion from a measured temperature increase, we need to understand the total heat capacity of the calorimeter, denoted as Ccal. This value is like a fingerprint of the calorimeter. It helps us grasp how much heat it can absorb and its response to temperature changes. The process to determine Ccal is ingenious. We burn a substance that releases a known amount of heat, like our friend benzoic acid. When exactly 1 gram of benzoic acid is combusted in a bomb calorimeter, it releases 26.38 kilojoules of heat. Now, imagine combusting 1 gram of benzoic acid in the calorimeter, and voila! The temperature rises by 4.857 degrees Celsius. By dividing the heat release, 26.38 kilojoules, by the temperature increase, 4.857 degrees Celsius, we get the heat capacity of the calorimeter, 5.431 kilojoules per degree Celsius. This is our Ccal value. Knowing Ccal is a game-changer. We can now use it to measure temperature changes from other reactions and calculate the heat evolved in those reactions, which is denoted as Crickson. The equation is simple yet powerful. Crickson equals negative Ccal multiplied by the temperature change, increment T. Let's move on to the next topic for more insights. Welcome back, students. Greetings, inquisitive learners. As we continue our journey, let's delve into the fascinating realm of thermodynamics and the intricate dance between heat and energy transformation. Picture this. Heat isn't just a random phenomenon, it's intricately linked to the transformation of energy. The first law of thermodynamics, often dubbed the law of energy conservation, states that energy cannot be created or destroyed, it can only change forms. That's an extraordinary concept right there. Now, here's where our friend calorimetry enters the spotlight again. Through the meticulous measurements we make using calorimeters, we're gaining insights into the energy changes occurring during chemical reactions. These insights are invaluable. They help us comprehend the energy transformations that underlie various natural processes and artificial creations. Think about it. From understanding the environmental impact of reactions to fine-tuning chemical processes, the knowledge we're gaining has real-world implications. So, let's keep our minds open, for this is a journey into the very essence of energy itself. Onward to the next topic. Greetings. Greetings, inquisitive learners. As we continue our journey, let's delve into the fascinating realm of thermodynamics and the intricate dance between heat and energy transformation. Picture this. Heat isn't just a random phenomenon, it's intricately linked to the transformation of energy. The first law of thermodynamics, often dubbed the law of energy conservation, states that energy cannot be created or destroyed, it can only change forms. That's an extraordinary concept right there. Now, here's where our friend calorimetry enters the spotlight again. Through the meticulous measurements we make using calorimeters, we're gaining insights into the energy changes occurring during chemical reactions. These insights are invaluable. They help us comprehend the energy transformations that underlie various natural processes and artificial creations. Think about it. From understanding the environmental impact of reactions to fine-tuning chemical processes, the knowledge we're gaining has real-world implications. So, let's keep our minds open, for this is a journey into the very essence of energy itself. Onward to the next topic. Greetings. Hello, everyone. Today, we're delving into the fascinating realm of reactions within a bomb calorimeter. These reactions take place under constant volume conditions, meaning that the heat transferred during these reactions directly corresponds to a change in internal energy, denoted as delta E. It's important to note that, typically, the difference between delta E and delta H, enthalpy change, is quite minuscule for most reactions. Let's put this into perspective with an example. In sample exercise 5.7, the difference between delta E and delta H is merely about 1 kilojoule per mole. That's a difference of less than 0.1%. While it is indeed possible to calculate delta H using delta E, we won't dwell on the specifics of these slight adjustments. Now, let's move on to our next intriguing topic. Hello, everyone. Welcome back, dear students. Our journey continues as we explore the relationship between heat transferred and changes in internal energy within the context of Bohm calorimeter reactions. Remember, the heat we measure in these reactions actually reflects a change in internal energy, increment E. Enthalpy change, increment H, on the other hand, is closely intertwined with internal energy change, increment E. As we dive deeper into the intricacies of these concepts, keep in mind that increment H accounts for heat exchange at constant pressure, while increment E reflects energy changes under constant volume conditions. It's a subtle yet significant distinction that adds layers of understanding to the world of thermodynamics. Now, let's proceed to the next topic and uncover more. Welcome back, dear. Greetings, inquisitive minds. Now, let's discuss a tantalizing possibility: calculating increment H, our enthalpy change, using the value of increment E, our internal energy change. While we won't delve into the technical intricacies, I want you to know that it is indeed possible. However, do remember that for such calculations, minor adjustments might be required. This insight further underlines how interconnected the various facets of energy within chemical reactions truly are. Keep your curiosity alive, for in the world of science, every piece of knowledge paves the way for even greater discoveries. Let's march forward to our next topic, where new horizons await. Greetings. Greetings, inquisitive minds. Now, let's discuss a tantalizing possibility: calculating increment H, our enthalpy change, using the value of increment E, our internal energy change. While we won't delve into the technical intricacies, I want you to know that it is indeed possible. However, do remember that for such calculations, minor adjustments might be required. This insight further underlines how interconnected the various facets of energy within chemical reactions truly are. Keep your curiosity alive, for in the world of science, every piece of knowledge paves the way for even greater discoveries. Let's march forward to our next topic, where new horizons await. Greetings. Hello again, students. Today, we're delving into the fascinating realm of body temperature regulation and the incredible mechanisms that keep us in balance. Think back to the times when someone asked you if you were running a fever. That seemingly simple question actually hints at the complexities within our bodies. Our body temperature fluctuates by just a few degrees, and these deviations can signify something being awry. Maintaining a nearly constant temperature is a crucial task for our bodies. Now, let's explore how our body's heating and cooling systems work by looking at it as a thermodynamic system. Imagine it as a delicate balance of energy. Our body's internal energy content increases when we consume food from our surroundings. These foods, such as glucose, C6H12, go through a process called metabolism, which is essentially controlled oxidation to produce CO2 and H2. This metabolic process releases energy, as indicated by the change in enthalpy, increment H equals -280Ht. This is just one piece of the puzzle, so let's keep uncovering the intricacies of our body's thermodynamics. Hello again, Welcome to Topic 3, where we're going to dive deeper into the concept of metabolism and how it ties into energy release and body temperature. Metabolism, which can be thought of as controlled oxidation, plays a pivotal role in our body's energy balance. Take glucose, C6H12O6, as an example. Through a series of chemical reactions, glucose is converted into carbon dioxide, and water. This process is not only about breaking down molecules but also about releasing energy. This energy is crucial for the functions our body performs, and it's closely linked to maintaining our body temperature. As chemical reactions take place, they release energy in the form of heat. This heat contributes to regulating our body's temperature, helping to keep it within that narrow range. Our body's incredible ability to manage these reactions is what allows us to function optimally. Now, let's keep exploring the remarkable world of thermodynamics within our bodies. Welcome to our fifth topic, where we're unraveling the connection between energy balance and maintaining equilibrium in our body. Just like how we aim to balance our budget, our body strives to balance energy intake and expenditure. Metabolism is a key player in this game of equilibrium. It helps us maintain a state of homeostasis, where everything is in balance. Did you know that temperature also influences our metabolism? When it's colder, our metabolic rate increases, producing more heat to keep us warm. On the other hand, when it's warmer, our metabolic rate tends to decrease to prevent overheating. Our body is incredibly adaptable, and it fine-tunes these processes based on the environment. Whether we're in a chilly winter or a scorching summer, our body knows how to respond to ensure our well-being. So, remember, maintaining the balance is essential, and our body's energy regulation is like a finely choreographed dance to keep us thriving. Keep your questions ready, because there's more to explore. Welcome back, students. Today, we're delving into the captivating topic of energy utilization within our own bodies. Did you know that approximately 40% of the energy our body produces is harnessed to perform essential functions like muscle contractions and nerve cell activities? The rest of the energy is transformed into heat. But don't think of this heat as just a waste. It plays a crucial role in maintaining our body temperature. When we generate excess heat, especially during intense physical activities, our body ensures balance by dissipating it into the surroundings. This fascinating process occurs through several mechanisms: radiation, convection, and evaporation. Think of radiation like a hot stovetop sending out heat to its cooler surroundings. Convection involves heating the air in contact with our body, causing it to rise and be replaced by cooler air, a constant cycle. You might be wondering how clothing plays a role in this. Well, in cold weather, warm clothing reduces the loss of heat through convection. Lastly, let's talk about evaporative cooling, a process you're familiar with when you sweat. When sweat evaporates from our skin, it takes away heat with it, cooling us down. Remember, perspiration is mostly water, so this cooling process involves the conversion of liquid water into water vapor, which is an endothermic reaction. Ready for more? Let's journey deeper into the fascinating world of energy transformations and their role in our lives. Welcome back, students. Hello, dear students. Today, we're going to uncover the captivating world of evaporative cooling and its connection to atmospheric humidity. As we journey through this topic, you'll discover why those scorching hot, humid days tend to make us feel more sweaty and uncomfortable. Let's delve right in. Evaporative cooling, a remarkable phenomenon, plays a crucial role in regulating temperatures. But here's the catch: the speed at which this cooling occurs actually decreases as atmospheric humidity increases. This is where the discomfort sets in on those muggy days. As humidity rises, the air is already holding a significant amount of moisture, making it more challenging for the moisture on our skin to evaporate effectively. This, my dear students, is why we often find ourselves feeling sweatier and less comfortable on those hot and humid occasions. So, remember, the relationship between evaporation speed and humidity is a key player in how our bodies respond to varying weather conditions. Fascinating, isn't it? Now, let's move forward to explore more about heat loss and its intriguing mechanisms. Hello, dear students. Welcome back, students. Today, we're on a quest to unravel the mysteries of heat loss mechanisms and how our body regulates temperature. As the temperature rises, our bodies employ fascinating strategies to keep us cool and comfortable. The first tactic involves a clever increase in blood flow near the surface of our skin. This may sound simple, but it's incredibly effective. You see, when we're feeling a bit too toasty, our blood vessels near the skin dilate, allowing more warm blood to flow closer to the surface. This proximity to the skin facilitates efficient heat transfer. As a result, the excess heat radiates from our body into the surrounding environment, providing us with a sense of relief. It's like our body's natural air conditioning system. But there's more. Our skin also becomes a key player in this process. It's through our skin that enhanced heat dissipation occurs, aided by the increased blood flow we just discussed. Together, these mechanisms help us manage our body temperature. So, the next time you find yourself enjoying a warm day, remember that your body is orchestrating this intricate dance to maintain a comfortable temperature. Now, let's continue our journey into the captivating world of temperature regulation. Welcome back. Welcome back, students. Today, we're on a quest to unravel the mysteries of heat loss mechanisms and how our body regulates temperature. As the temperature rises, our bodies employ fascinating strategies to keep us cool and comfortable. The first tactic involves a clever increase in blood flow near the surface of our skin. This may sound simple, but it's incredibly effective. You see, when we're feeling a bit too toasty, our blood vessels near the skin dilate, allowing more warm blood to flow closer to the surface. This proximity to the skin facilitates efficient heat transfer. As a result, the excess heat radiates from our body into the surrounding environment, providing us with a sense of relief. It's like our body's natural air conditioning system. But there's more. Our skin also becomes a key player in this process. It's through our skin that enhanced heat dissipation occurs, aided by the increased blood flow we just discussed. Together, these mechanisms help us manage our body temperature. So, the next time you find yourself enjoying a warm day, remember that your body is orchestrating this intricate dance to maintain a comfortable temperature. Now, let's continue our journey into the captivating world of temperature regulation. Welcome back, students. Hello again, students. Let's delve into another captivating topic: temperature regulation and the intriguing concept of hypothermia. Our bodies are truly remarkable systems that strive to maintain a balance. When the body temperature drops too low, a clever response kicks in. Blood flow to the skin surface is reduced, which helps to minimize heat loss. But that's not all. Our bodies also have an incredible mechanism known as shivering. When temperatures plummet, small involuntary muscle contractions, or shivering, are triggered. Now, here's the fascinating part. The very biochemical reactions that provide the energy for these contractions also generate heat. It's like our body's own internal heating system. However, if the body can't successfully uphold its normal temperature, a highly dangerous condition known as hypothermia can develop. Hypothermia occurs when the body's core temperature drops to a perilously low level. This can have severe consequences for our health and well-being. Let's proceed to our next topic to uncover more about these remarkable processes. Hello again, welcome to our third topic, dear students. Today, we're peeling back the layers of the incredible science behind shivering and energy generation. Imagine being out in the cold. Your body reacts with shivers, right? It's a clever way our body tries to warm up. These shivers are actually small, involuntary muscle contractions. Now, here's where things get really interesting. For these contractions to occur, our body needs energy. And where does this energy come from? Biochemical reactions within our cells. These reactions are like miniature powerhouses, generating the energy required for the contractions. But wait, there's an extra bonus. These reactions also release heat as a byproduct. So, not only do the contractions generate energy for our muscles, but they also provide much-needed warmth. It's a win-win situation for our body in chilly times. Let's move forward to uncover more about how our body maintains its equilibrium. Welcome to our third. Alright, dear students, let's delve deeper into the concept of hypothermia on this fourth topic. Our body's temperature regulation system is a marvel, but it's not infallible. Sometimes, the body struggles to maintain its normal temperature, and that's when hypothermia rears its ugly head. Hypothermia occurs when our core body temperature drops dangerously low. This can lead to a range of symptoms, including confusion, drowsiness, and a slowed heart rate. In severe cases, it can even result in organ failure and, sadly, death. It's a stark reminder of how crucial it is for us to ensure our bodies are properly protected in cold conditions. This includes wearing appropriate clothing and seeking shelter when necessary. Hypothermia serves as a potent reminder of the delicate balance our bodies maintain, and how crucial it is to take care of ourselves, especially in harsh weather conditions. Stay warm and stay safe, everyone. Let's continue our exploration of the incredible ways our bodies respond to different situations. Alright, Dear Welcome back, students. Today, we're delving into an intriguing concept in chemistry known as Hess's law. Just like a fish ladder provides fish with an alternative route around an obstruction, Hess's law offers us an alternative route to determine enthalpy changes in certain chemical reactions. You see, there are instances where calculating the enthalpy change directly might be challenging, but fear not. Hess's law comes to the rescue. It enables us to calculate these changes by utilizing data that's easier to obtain. Just as fish find a way to reach their destination despite obstacles, Hess's law helps us navigate through complex chemical reactions. Let's explore this concept further. Welcome back, students. Hello again, students. Let's dive deeper into how Hess's law actually works. Imagine you're faced with a complex chemical reaction, and determining its enthalpy change seems like a daunting task. That's where Hess's law steps in. We can break down this complicated reaction into a series of simpler reactions for which we know the enthalpy changes. It's like solving a puzzle by working with smaller, manageable pieces. By summing up the enthalpy changes of these simpler reactions, we can find the enthalpy change of the desired reaction. This approach allows us to tackle complex scenarios step by step, just like a fish ladder helps fish overcome obstacles. Hello again, Great job following along, students. To solidify our understanding, let's draw a parallel between the fish ladder concept and Hess's law. Just as a fish ladder offers fish an alternative route to their destination, Hess's law provides us an alternative route to calculate enthalpy changes. When a chemical reaction seems difficult to tackle directly, we can take a detour by considering other reactions with known enthalpy changes. This approach lets us overcome the obstacles that might have initially made enthalpy change calculations seem challenging. With Hess's law, we're equipped with a powerful tool to navigate the intricate world of chemical reactions. Thank you for your attention, and keep up the great work. Great job following. You're doing fantastic, students. Now, let's see Hess's law in action with some practical examples. Imagine you have a complex reaction, and you need to find its enthalpy change. Step 1. Identify simpler reactions with known enthalpy changes. Step 2. Manipulate these reactions, if necessary, so they align with the desired reaction. Step 3. Add up the enthalpy changes of these simpler reactions to get the enthalpy change of the desired reaction. Voila! You've successfully utilized Hess's law. This approach is incredibly versatile and can be applied to various chemical reactions, giving us insights into energy changes that occur during these processes. Just like a fish ladder offers different paths, Hess's law empowers us to navigate through the complexities of chemistry. You're doing Bravo, students! We've reached the end of our exploration of Hess's law and its fascinating applications. Remember, just as a fish ladder provides fish an alternative route, Hess's law provides us with a strategic pathway to calculate enthalpy changes in complex chemical reactions. By breaking down intricate reactions into simpler steps, we can navigate through challenges and arrive at accurate results. So, whether you're considering fish overcoming obstacles or chemical reactions overcoming enthalpy change difficulties, the underlying principle remains the same: finding a way to your goal, even when faced with challenges. Keep up the excellent work, and let's continue our journey through the captivating world of chemistry. Bravo! Welcome back, students. In our last topic, we delved into energy production examples. Today, let's shift our focus to the intriguing world of enthalpy and its fascinating properties. Enthalpy, being a state function, means that the change in enthalpy, delta H, associated with any chemical process solely relies on the amount of matter involved and the initial and final states of the reactants and products. This means that regardless of whether a reaction occurs in a single step or multiple steps, the sum of enthalpy changes from individual steps remains consistent with the enthalpy change of the overall process. Let's dive deeper with an example. Imagine the combustion of methane gas, CH, to form carbon dioxide, CO, and water, HO. This reaction can be viewed as a single-step process or as a two-step process involving combustion and condensation. However, the enthalpy change for the complete reaction remains the same, whether we consider it in one step or two. The enthalpy change for the overall process is a sum of the enthalpy changes for these individual steps. So, the concept of state functions allows us to understand the energy changes within chemical processes in a consistent manner, regardless of their complexity. Let's move on to explore more intriguing aspects of chemical reactions and energy. Welcome back, students. In our journey through energy and chemical reactions, we're now venturing into the realm of Hess's law and enthalpy changes. Now, pay close attention because this concept is quite remarkable. Hess's law comes to our rescue when we need to calculate enthalpy changes for reactions. You might wonder how? Well, we can actually determine the increment H for a reaction by using the tabulated increment H values of other reactions. This means we don't always need to conduct calorimetric measurements for every single reaction. Think of it as a way to simplify our work while still getting accurate results. Let's move on to understand this concept better. Welcome back, students. In our last topic, we delved into energy production examples. Today, let's shift our focus to the intriguing world of enthalpy and its fascinating properties. Enthalpy, being a state function, means that the change in enthalpy, increment H, associated with any chemical process solely relies on the amount of matter involved and the initial and final states of the reactants and products. This means that regardless of whether a reaction occurs in a single step or multiple steps, the sum of enthalpy changes from individual steps remains consistent with the enthalpy change of the overall process. Let's dive deeper with an example. Imagine the combustion of methane gas, CH4, to form carbon dioxide, CO2, and water, H2O. This reaction can be viewed as a single-step process or as a two-step process involving combustion and condensation. However, the enthalpy change for the complete reaction remains the same, whether we consider it in one step or two. The enthalpy change for the overall process is a sum of the enthalpy changes for these individual steps. So, the concept of state functions allows us to understand the energy changes within chemical processes in a consistent manner, regardless of their complexity. Let's move on to explore more intriguing aspects of chemical reactions and energy. Welcome back, students. Hello again, dear students. Today, we're delving into the intriguing world of enthalpy changes and a principle known as Hess's law. Imagine this as a guiding star for understanding the energy changes within chemical reactions. According to Hess's law, if a reaction takes place in a series of steps, the overall enthalpy change, increment H, is the sum of the enthalpy changes for each individual step. Fascinating, isn't it? This principle also highlights that the total energy change is not affected by the number of steps or the specific path taken during the reaction. The beauty of this law lies in the concept of enthalpy being a state function, meaning it only depends on the initial and final states of the reaction, not the path itself. Now, what does this mean practically? It means we can calculate the enthalpy change for any process, as long as we know the increment H values for each step along the way. This knowledge opens the door to predicting energy changes for a wide range of reactions with just a handful of experimental measurements. Isn't that an efficient way to understand the energy world around us? Hello again, dear students. Today, we're venturing into the realm of energy calculations with an incredibly useful tool known as Hess's law. This concept comes in handy when we encounter energy changes that are tricky to measure directly. Let's consider an intriguing example. Imagine trying to measure the enthalpy change for the combustion of carbon to form carbon monoxide. A direct measurement is quite the challenge because, during the combustion, some carbon remains unreacted due to the formation of both CO and CO2. However, fear not. We have a solution. Both solid carbon and carbon monoxide can be fully burned in oxygen to yield carbon dioxide. By using the enthalpy changes of these reactions, we can cleverly calculate the heat of combustion of carbon. This technique is beautifully illustrated in sample exercise 5.8. So, let's unravel the mysteries of Hess's law and its power in indirectly determining energy changes. Hello, dear Welcome back, curious minds. Our exploration of Hess's law continues as we confront the challenges of directly measuring certain energy changes. One compelling case is the combustion of carbon to form carbon monoxide. This seemingly simple process becomes a puzzle due to the presence of unreacted carbon. When carbon reacts with oxygen to produce both CO and company, we're left with some carbon that hasn't participated in the reaction. This unreacted carbon adds complexity to measuring the energy change accurately. But don't despair. With the ingenious approach provided by Hess's law, we're equipped to conquer such complexities. Stay with me as we uncover the secrets behind indirect measurements and their significance in the world of energy calculations. Welcome back. Welcome back, curious minds. Our exploration of Hess's law continues as we confront the challenges of directly measuring certain energy changes. One compelling case is the combustion of carbon to form carbon monoxide. This seemingly simple process becomes a puzzle due to the presence of unreacted carbon. When carbon reacts with oxygen to produce both CO and CO2, we're left with some carbon that hasn't participated in the reaction. This unreacted carbon adds complexity to measuring the energy change accurately. But don't despair. With the ingenious approach provided by Hess's law, we're equipped to conquer such complexities. Stay with me as we uncover the secrets behind indirect measurements and their significance in the world of energy calculations. Welcome back. Welcome back, curious minds. Our exploration of Hess's law continues as we confront the challenges of directly measuring certain energy changes. One compelling case is the combustion of carbon to form carbon monoxide. This seemingly simple process becomes a puzzle due to the presence of unreacted carbon. When carbon reacts with oxygen to produce both CO and CO2, we're left with some carbon that hasn't participated in the reaction. This unreacted carbon adds complexity to measuring the energy change accurately. But don't despair. With the ingenious approach provided by Hess's law, we're equipped to conquer such complexities. Stay with me as we uncover the secrets behind indirect measurements and their significance in the world of energy calculations. Welcome back. Hello once again, my curious learners. Today, we're embarking on a journey through the world of enthalpy changes and heat calculations. Hold on to your scientific hats. We've learned about combustion reactions and energy production. Now, let's delve into a powerful tool called standard enthalpies of formation. These values allow us to calculate enthalpy changes for various reactions. Imagine the wealth of information we can gain from tables filled with increment H values. We're talking about enthalpies of vaporization, which show us the energy required to transform liquids into gases, or enthalpies of fusion, revealing the energy needed to melt solids. And that's not all. Consider enthalpies of combustion, which describe the energy released when a substance burns in oxygen. Now, one of the cornerstones of thermochemical data is the enthalpy of formation, often abbreviated as increment HF. This is a crucial value that tells us the energy change when a compound is formed from its elemental components. Keep that F in mind. It signifies formation from elements. So, Buckle up as we venture deeper into the world of heat calculations and thermochemical data. Hello once again. Welcome back, inquisitive minds. Let's explore the concept of enthalpy of formation in greater detail. Picture this. When a compound is formed from its building blocks, the enthalpy changes. This change is what we call the enthalpy of formation, increment h. It's like capturing the energy transformation that happens during a compound's creation. Now, why is this significant, you ask? Well, increment h holds the key to understanding the energy stored within a compound. By knowing this value, we gain insights into how stable or reactive a substance might be. Remember, the magic word here is formation. When a substance is formed from its constituent elements, we're talking about increment h. This simple yet profound concept unravels the mysteries of energy changes in compounds. So, let's march forward and explore the applications of this knowledge. Welcome back. Fantastic to see you all engaged. Now, let's roll up our sleeves and put our newfound knowledge into action. Enthalpy of formation isn't just a concept, it's a tool. We can use it to calculate the heat of reaction. How? Well, imagine having a chemical equation at hand. By utilizing the increment h values of the substances involved, we can determine the enthalpy change. Balancing chemical equations, as you've learned, is crucial here. Remember, reactions maintain a delicate balance of atoms on both sides. This balance extends to energy as well. When we sum up the increment h values of the reactants and products, we obtain the enthalpy change of the reaction. Isn't it incredible how we can quantify energy changes through these calculations? Keep your minds sharp, as we're about to dive into real examples and practice these calculations firsthand. Fantastic to see. Welcome back, eager learners. Now that we've grasped the intricacies of enthalpy changes and calculations, let's see how this knowledge makes a real impact. We're not just dealing with abstract concepts here. These principles are the backbone of various industries and technologies. From understanding the energy shifts during chemical reactions to optimizing energy efficiency in industrial processes, thermochemical data is invaluable. Think about it. Industries rely on this data to fine-tune their processes and minimize energy waste. As we advance technologically, innovations in energy production and consumption are largely driven by the insights gained from enthalpy changes. We're on the cusp of a more sustainable and energy-conscious world, thanks to the groundwork laid by these very principles. So, get ready to be part of a brighter, energy-efficient future. Welcome back. Hello, everyone. Today, we're delving into a fundamental concept in thermodynamics: enthalpy change and the significance of standard states. Enthalpy change, as we've learned, isn't a fixed value, it's influenced by several factors. Temperature, pressure, and the state of reactants and products all play a role in determining the magnitude of this change. To make meaningful comparisons between different reactions, we establish a set of conditions called a standard state. This standard state serves as our reference point and provides consistency for tabulating enthalpies. Now, what exactly is this standard state? Well, it's the pure form of a substance under atmospheric pressure, usually at a temperature of 298 K or 25 degrees Celsius. This temperature choice aligns with our need for a common benchmark. When all reactants and products are in their standard states, we define the resulting enthalpy change as the standard enthalpy change, increment h degree. The degree symbol signifies that these measurements are made under standard state conditions. This concept is pivotal in understanding and comparing various reactions. So, let's keep moving forward to uncover more about enthalpy changes and their connections to chemical reactions. Hello, everyone. Welcome back, everyone. Now, let's dive a bit deeper into the factors affecting enthalpy change, temperature and pressure. Picture this. As the temperature rises, molecules gain kinetic energy, resulting in more energetic and dynamic reactions. This translates to varying enthalpy changes as temperature shifts. Similarly, pressure also influences enthalpy, especially when we're dealing with gaseous substances. Altering pressure can lead to changes in the volume and behavior of gases, which in turn impact the enthalpy change. To make accurate predictions and understand how these variables interplay, we need to explore these factors thoroughly. So, as we proceed, remember that enthalpy change isn't a static value. It dances to the tune of temperature and pressure variations. Welcome back. Hello again, curious minds. Now, let's unravel why the concept of standard state is so significant. As we discussed earlier, the standard state is a specific set of conditions that allow us to make accurate and meaningful comparisons of enthalpies across different reactions. It's like having a common language for the thermodynamic world. This state represents the pure form of a substance under atmospheric pressure, typically at 100 kilopascals, and a chosen temperature, which is usually 298 K. By adopting this standard state, we ensure that we're all on the same page when it comes to measuring and discussing enthalpy changes. It provides a uniform reference point, making our calculations and predictions more reliable and consistent. So, let's continue our journey of exploring the intricacies of enthalpy change and its connection to chemical reactions. Hello again. Welcome back, eager learners. Let's zoom in on a critical concept: standard enthalpy change, delta H. This value is essentially the enthalpy change that occurs when all reactants and products are in their respective standard states. The delta H symbol attached to delta H reminds us that this measurement is made under standard state conditions. Think of it as a benchmark, a reference point that enables us to compare enthalpies of different reactions. This concept forms the backbone of our ability to understand and analyze the energy changes associated with chemical reactions. Keep in mind that this understanding will serve as a foundation as we delve further into the captivating world of thermodynamics. Welcome back. Hello, dear students. Today, we're delving into a critical concept in thermodynamics: the standard enthalpy of formation, often denoted as delta H, often written as increment H. Enthalpy, as you might recall, refers to the heat content of a system. Now, when we talk about the increment H, we're essentially exploring the change in enthalpy that occurs when 1 mole of a compound is formed from its elements, and this happens with all substances being in their standard states. It's like witnessing the birth of a new compound from its elemental building blocks, and this change in enthalpy is our focus. Oh, and don't forget, we frequently report these increment H values at 298 Kelvin, which is room temperature. Now, here's a fascinating detail. If an element exists in different forms under standard conditions, we usually use the most stable form of that element for our formation reaction. Let's take an example to solidify this. Imagine we want to find the increment H for ethanol, CHO. We're interested in the reaction where 2 moles of carbon in its stable graphite form, 3 moles of hydrogen gas, and half a mole of oxygen gas come together to form 1 mole of ethanol. The enthalpy change for this reaction is -277.7 kilojoules, and it signifies the energy change when ethanol is born from its elemental components. Now that's some energy transformation worth exploring. Ready for more? Let's move on. Hello, dear students. Today, we're delving into a critical concept in thermodynamics: the standard enthalpy of formation, often denoted as increment HF degree. Enthalpy, as you might recall, refers to the heat content of a system. Now, when we talk about the increment hf degree, we're essentially exploring the change in enthalpy that occurs when 1 mole of a compound is formed from its elements, and this happens with all substances being in their standard states. It's like witnessing the birth of a new compound from its elemental building blocks, and this change in enthalpy is our focus. Oh, and don't forget, we frequently report these increment hf degree values at 298 K, which is room temperature. Now, here's a fascinating detail. If an element exists in different forms under standard conditions, we usually use the most stable form of that element for our formation reaction. Let's take an example to solidify this. Imagine we want to find the increment hf degree for ethanol, C2H5 oxygen monohydride. We're interested in the reaction where 2 moles of carbon in its stable graphite form, 3 moles of hydrogen gas, and half a mole of oxygen gas come together to form 1 mole of ethanol. The enthalpy change for this reaction is -277.7 kilojoules. And it signifies the energy change when ethanol is born from its elemental components. Now that's some energy transformation worth exploring. Ready for more? Let's move on. Hello, dear students. Today, we're delving into the intriguing realm of elemental stability and the concept of standard states. Our adventure starts with oxygen, an essential element. Did you know that the most stable form of oxygen is O2? This molecular form remains stable at 298 K and atmospheric pressure. Similarly, carbon takes center stage with its 2 well-known forms, graphite and diamond. At 298 K and atmospheric pressure, graphite is the stable form. Now, let's focus on hydrogen, a crucial element for many reactions. The most stable form of hydrogen under standard conditions is H2, which is used in various equations, like equation 5.25. What's fascinating about formation reactions is that they consistently produce 1 mole of the desired substance, just like in equation 5.25. Remember, we'll be discussing standard enthalpies of formation in kilojoule per mole of the substance formed. Get ready to explore more intriguing details in our upcoming topics. Hello again, bright minds. In our ongoing exploration, we encounter the captivating concept of the standard enthalpy of formation. This value represents the energy change that occurs when 1 mole of a substance forms from its elements under standard conditions. Now, pay close attention to the units. These values are reported in kilojoules per mole of the substance formed. For a quick reference, you'll find some values in Table 5.3. If you're hungry for more data, don't worry, Appendix C has an extensive collection. So, remember, each value provides insights into the energy involved in forming compounds from their elemental constituents. Let's keep our energy high as we venture further. Hello again. Greetings, inquisitive learners. We're about to unlock a fascinating secret about standard enthalpies of formation. Brace yourselves for this insight. The standard enthalpy of formation for the most stable form of any element is exactly 0. Why, you ask? Well, it's because there's no formation reaction needed when an element is already in its standard state. Isn't that remarkable? This principle applies to elements like carbon in its graphite form, hydrogen as H2, oxygen in O2, and other elements in their standard states. So, remember, when an element is already in its natural habitat, so to speak, there's no energy change involved in forming it. Stay curious as we journey onward. Greetings. Welcome, students. Today, we're delving into the fascinating world of enthalpy changes and a powerful concept known as Hess's law. Enthalpy changes, represented by increment h, provide insights into the energy exchange during chemical reactions. To better understand these changes, we often employ subscripts, as seen here, to keep track of connections between reactions and their respective increment h values. Now, what's truly remarkable is how Hess's law comes into play. This law allows us to manipulate chemical equations and combine them to calculate standard enthalpy changes. Let's take a closer look at equation 5.29, where we've utilized Hess's law to express the standard enthalpy change as the sum of increment h values from equations 5.26 through 5.28. Using data from table 5.3, we can calculate increment h degree Rxn for this reaction. This involves adding up the individual increment h values for each component. Increment hf degree 3c3h81g24, 3 increment hf degree 3co21g24, and 4 increment hf degree 3h201l24. After plugging in the numbers, we find that increment h degree Rxn equals -2220 kilojoules. The enthalpy diagram in figure 5.23 visually represents the components of this calculation. During step 1, the reactants break down into their elemental constituents in standard states. Steps 2 and 3 involve the formation of products from these elements. Remember, our approach here aligns with the guidelines we discussed in section 5.4. So, as we venture further, keep in mind the fascinating interplay of enthalpy changes and Hess's law in understanding energy transformations during chemical reactions. Welcome, student. Welcome, students. Today, we're delving into the fascinating world of enthalpy changes and a powerful concept known as Hess's law. Enthalpy changes, represented by delta H, provide insights into the energy exchange during chemical reactions. To better understand these changes, we often employ subscripts, as seen here, to keep track of connections between reactions and their respective delta H values. Now, what's truly remarkable is how Hess's law comes into play. This law allows us to manipulate chemical equations and combine them to calculate standard enthalpy changes. Let's take a closer look at equation 5.29, where we've utilized Hess's law to express the standard enthalpy change as the sum of delta H values from equations 5.26 through 5.28. Using data from table 5.3, we can calculate delta H degree for this reaction. This involves adding up the individual delta H values for each component. Delta H degree, 3Ch, 3 delta H degree, 3Co, and 4 delta H degree, 3Ho. After plugging in the numbers, we find that delta H degree equals -2220 kilojoules. The enthalpy diagram in figure 5.23 visually represents the components of this calculation. During step 1, the reactants break down into their elemental constituents in standard states. Steps 2 and 3 involve the formation of products from these elements. Remember, our approach here aligns with the guidelines we discussed in section 5.4. So, as we venture further, keep in mind the fascinating interplay of enthalpy changes and Hess's law in understanding energy transformations during chemical reactions. Welcome, student. Hello, students. Today, we're delving into an important concept known as decomposition and its relation to enthalpy change. Our journey takes us to equation 5.26, which interestingly, is the reverse of the formation reaction for C3H8. Now, when we talk about decomposition, we're essentially discussing the breakdown of a compound into its constituent elements or simpler compounds. In this case, the decomposition reaction involves propane, C3H8. What's intriguing is that the enthalpy change for this particular decomposition reaction is the negative of the increment HF degree value for the propane formation reaction. Enthalpy change is a crucial aspect of chemical reactions as it indicates the heat exchange involved. So, as we explore this decomposition reaction further, remember that understanding enthalpy changes gives us insights into the energy transformations within chemical reactions. Hello, students. Welcome back, students. As we continue our exploration of enthalpy, let's focus on the relationship between enthalpy change and heat exchange. Enthalpy change represents the amount of heat energy involved in a chemical reaction. Now, here's the interesting part. Reactions can be classified as exothermic or endothermic. In exothermic reactions, heat is released into the surroundings, resulting in a negative enthalpy change. On the other hand, endothermic reactions absorb heat from the surroundings, leading to a positive enthalpy change. But how do we keep track of these changes? Well, we have sign conventions. A negative increment H indicates an exothermic reaction, while a positive increment H signifies an endothermic reaction. Remember, these conventions help us interpret the energy flow in chemical processes. So, as we venture further, think about how enthalpy changes offer us insights into the heat dynamics of reactions. Welcome back, students. Welcome to our next exciting chapter, dear students. Today, we're delving into the captivating world of redox reactions and how they power some of our modern devices. Redox stands for reduction oxidation, and these reactions are all about the exchange of electrons between species. And guess what? Batteries, those little powerhouses that keep our devices running, rely on redox reactions. Within a battery, oxidation and reduction processes occur, resulting in the generation of electrical energy. This energy is what powers our gadgets, from smartphones to laptops. The beauty lies in the electron dance. As one substance loses electrons, oxidation, another gains them, reduction. This flow of electrons is what gives us the electric current we need. So, as we unravel the intricacies of redox reactions, remember that these processes are at the heart of many of our technological advancements. Welcome back, everyone. In our previous topic, we got a glimpse of how enthalpy changes impact chemical reactions. Now, let's dive deeper into the world of energy transformations. Enthalpy changes are closely related to heat exchange during reactions. They allow us to understand the amount of energy involved in various chemical processes. This knowledge is invaluable because it helps us predict and control reactions, as well as optimize industrial processes. By studying the enthalpy changes, we can gain insights into the direction a reaction will take and the energy it will release or absorb. This connection between chemical reactions and enthalpy changes is a fundamental concept in thermodynamics. Keep in mind that these concepts are like keys that unlock the mysteries of energy transformations. Now, let's proceed to the next topic to uncover another captivating example. Welcome back, everyone. Great to have you with us, students. Today, we're embarking on an exploration of how enthalpy changes can be harnessed for practical applications. Our understanding of energy flow in chemical systems allows us to optimize reactions for various purposes. By comprehending enthalpy changes, we can adjust reaction conditions to maximize the desired product or minimize energy losses. This knowledge is crucial in industries like pharmaceuticals, where precise control over reactions is essential. Imagine the impact on our daily lives from the medicines we take to the materials used in technology. Enthalpy changes play a pivotal role. So, as we progress through our study, remember that these insights hold the key to manipulating chemical reactions in ways that benefit us all. Ready for more? Let's proceed to our next enlightening topic. Great to have you with. Hello again, curious minds. Our journey continues as we delve into an essential topic: differentiating between physical and chemical changes. As we've seen, chemical reactions involve the rearrangement of atoms and the formation of new substances. This alteration of chemical composition sets chemical changes apart from physical changes, where only the physical properties of substances are affected. To understand this better, think about rust forming on iron, a chemical change, versus ice melting into water, a physical change. These concepts are vital because they help us recognize when new substances are formed and when substances maintain their original identity despite appearing different. This insight is the cornerstone of understanding the transformations that matter undergoes. Ready to explore more? Let's move on to our next topic. Hello again, curious minds. Today, we're uncovering a practical application of energy changes, batteries. These devices are all around us, powering our devices and vehicles. Batteries work through redox reactions, where electrons are transferred between substances. This transfer generates electrical energy that we can harness. The key players in batteries are the anode and cathode, each facilitating a different part of the redox reaction. As you can see, understanding energy changes has real-world implications, making our lives more convenient and efficient. So, let's charge up our knowledge further by diving into the specifics of battery functioning on our next topic. Hello. Welcome back, students. Our exploration of energy changes continues with a focus on their impact in our daily lives. From heating our homes and cooking our meals to powering our electronic devices, energy changes are at the heart of these processes. These changes are not just scientific concepts, they're deeply intertwined with our everyday experiences. By understanding the role of energy changes, we can make informed decisions about conserving energy, using resources efficiently, and even designing technologies that enhance our lives. So, as we move forward, keep in mind that the knowledge we're gaining has the power to shape the way we interact with the world around us. Ready for more insights? Let's proceed to our next engaging topic. Welcome back, students. Bravo! Dear students, for embarking on this remarkable journey through the world of energy transformations and chemical reactions. Today, we've explored the nuances of enthalpy change, formation reactions, and their profound impact on our understanding of chemistry. Remember, chemistry is more than just elements and compounds, it's the dance of energy and matter on the molecular stage. As we conclude this session, keep in mind that our exploration has only scratched the surface. The realm of chemistry holds countless mysteries waiting to be uncovered. Until next time, keep your curiosity alive and your passion for learning burning bright. Bravo! Now, let's talk about the backbone of these equations, the stoichiometric coefficients, represented by n and m. These coefficients hold immense importance as they tell us about the relative amounts of substances involved in a reaction. Think of them as the recipe proportions for a chemical reaction. Just like a chef needs the right amounts of ingredients, chemical reactions need balanced amounts of reactants and products to work efficiently. Balancing equations using stoichiometric coefficients ensures that no atom is created or destroyed in the process. It's like following a strict budget. Every element's quantity has to match up. This balancing act is fundamental to understanding and predicting chemical reactions. Now, Alright, students. Let's dive deeper into the components of equation 5.31. Remember, the first term on the right side of the equation deals with the formation reactions of the products. Think of it like this: elements coming together to create the products we're interested in. These reactions occur in the forward direction, following the chemical equation. This concept isn't new. It's quite similar to what we've seen in equations 5.27 and 5.28. Just like a puzzle fitting into place, atoms and molecules interact to form new substances. Let's keep this analogy in mind as we explore further. Alright, student. Moving on, students. We're now entering the realm of the second term in equation 5.31. This term deals with the reverse of the formation reactions, but for the reactants this time. Just like looking at a process in reverse motion, this term explores how reactants can break down to form elements. You might recall equation 5.26, which involves a similar concept. And here's something interesting: you'll notice a minus sign before this term. This minus sign indicates that we're looking at the reverse direction. Imagine rewinding a video to see how the reactants were originally formed. It's this kind of intricate understanding that helps us decipher the mysteries of chemical equations. Moving on, Now, let's talk about the backbone of these equations, the stoichiometric coefficients, represented by n and m. These coefficients hold immense importance as they tell us about the relative amounts of substances involved in a reaction. Think of them as the recipe proportions for a chemical reaction. Just like a chef needs the right amounts of ingredients, chemical reactions need balanced amounts of reactants and products to work efficiently. Balancing equations using stoichiometric coefficients ensures that no atom is created or destroyed in the process. It's like following a strict budget: every element's quantity has to match up. This balancing act is fundamental to understanding and predicting chemical reactions. Now, before we wrap up for today, let's take a moment to recap what we've learned. We explored the sigma symbol, which represents the sum of stoichiometric coefficients, like n and m, give us insights into the quantities of substances involved in a reaction. Equation 5.31 dissected the formation reactions of products and the reverse of these reactions for reactants. Remember, these terms are like puzzle pieces fitting together to create a complete picture of chemical processes. Understanding these concepts is essential as we journey further into the realm of chemistry. In our next session, get ready to dive into an exciting topic that builds upon the foundations we've established today. Keep up the great work, and I'll see you soon. Before we wrap up Hello again, young minds. Today, we're unwrapping the connection between bond enthalpies and gas phase reactions. The data we work with mostly originates from reactions involving gases. Why is this significant, you ask? Well, gas phase reactions are often more well-defined and easier to study. This, in turn, contributes to the accuracy of our estimations when it comes to enthalpy changes. When gases react, it's relatively simpler to determine how bonds break and form. This data is like a treasure trove for understanding energy changes. Hello again, young Greetings, knowledge seekers. As we continue our exploration of bond enthalpies, let's address a challenge: reactions in liquids and solids. Here's the deal. While the bond enthalpy data thrives in the gas phase, things get a bit trickier in the realm of liquids and solids. Why, you wonder? Well, the interactions in these condensed phases are far more complex. Different molecular environments can lead to inaccuracies in our estimations. Intermolecular forces play a pivotal role here, and understanding them is like deciphering the code to accurate predictions. Greetings. Welcome to the grand finale of our bond enthalpy journey. Remember, even with its limitations, bond enthalpy data is a treasure trove of knowledge. It might not be perfect, but it's far from useless. We can still make valuable approximations of energy changes using this data. It's like a trusty tool for comparing how different reactions stack up in terms of energy changes. And guess what? This knowledge forms the foundation of understanding chemical reactions. By mastering this, you're opening doors to more advanced explorations in the fascinating world of thermodynamics. So, keep those minds curious and those spirits ignited. Welcome to the grand. Good day, students. Today, we're diving into the captivating world of energy production and some fascinating examples. Our journey begins by exploring various sources of energy creation. One remarkable process is the combustion reaction, where the interaction between fuel and oxygen results in the creation of expanding gases. These gases, in turn, perform work, such as powering a car's engine. But that's just the start. Let's also journey into the world of champagne production. Here, yeasts employ chemical reactions to convert sugars into ethanol and carbon dioxide, creating those delightful bubbles we associate with celebrations. The pressure built up in a corked champagne bottle can even be harnessed to do work. Our final example brings us to batteries. Within them, redox reactions occur, generating electrical energy that proves incredibly useful for various applications. As we explore these examples, keep in mind that all forms of energy can be categorized as either kinetic or potential energy. The energy originating from chemical reactions primarily involves changes in potential energy. This type of energy emerges from the electrostatic interactions happening at the atomic level. Now, let's journey further into the intricacies of energy and chemical reactions. Good day, students. Welcome back, dear students. In our journey of understanding energy changes within chemical reactions, we're now delving into the realm of bond energies and how they relate to enthalpy changes. Imagine energy as a key player during chemical reactions. Breaking bonds requires energy input, while forming bonds releases energy. By measuring the enthalpy change of a reaction and analyzing the bonds involved, we can assign specific values to these bonds. Let's introduce the concept of bond enthalpy. It's the energy change, increment h, needed to break a single bond in 1 mole of a gaseous substance. This concept shines when we encounter simpler reactions like the dissociation of Cl, G. This diatomic molecule is united by a single covalent bond, chlorine-chlor. When this bond is broken, the Cl molecule splits into chlorine atoms, and this energy change is quantified by the bond enthalpy. Now, let's dive even deeper into this enthralling world. Welcome back, dear. Hello again, bright minds. Today, we're focusing on a specific example to grasp the concept of bond enthalpy even better. Picture a Cl2 molecule held together by a covalent bond, Cl2. Now, let's say we subject this molecule to dissociation, breaking it into 2 individual chlorine atoms. This process involves breaking the Cl2 bond. The energy needed for this bond breaking is a crucial piece of information, and that's where bond enthalpy steps in. By measuring the enthalpy change during this reaction and understanding the bonds at play, we can calculate the bond enthalpy for the Cl2 bond. Remember, breaking bonds requires energy, and that energy can be quantified. As we move forward, keep in mind that these principles extend to more complex reactions as well. Get ready for more exciting revelations. Hello again, greetings, inquisitive minds. Let's expand our understanding of bond enthalpies and how they contribute to energy calculations within reactions. Think of bond enthalpies as our trusty tools. They reveal the energy required for breaking bonds and the energy released when forming new ones. Every reaction involves a give and take of energy due to these bond changes. Now, when we sum up the energy required to break bonds and the energy released during bond formation, we get the net energy change for the entire reaction. This concept is vital because it helps us estimate the overall enthalpy change for a chemical reaction. Our journey into the intricacies of energy continues, so stay curious and engaged. Greetings. Hello, knowledge seekers. We're taking our knowledge of bond enthalpies to the next level. Remember, this concept isn't limited to simple diatomic molecules like Cl2. It applies to complex molecules as well. Imagine molecules with multiple bonds. We can calculate bond enthalpies for each of these bonds. For instance, let's consider methane, CH4. In its combustion reaction, not just 1, but 4 C, H bonds are broken, and 4 new C, O bonds are formed. By calculating the energy changes associated with these bond alterations, we gain a comprehensive understanding of the energy dynamics within the reaction. This approach empowers us to estimate the overall enthalpy change accurately. As we conclude this section, remember that bond enthalpies are valuable tools in our quest to decipher the secrets of energy transformations in chemistry. Hello. Good day, students. Today's topic is all about bond enthalpy and how it ties in with energy changes during chemical reactions. We'll dive into some intricate details, so make sure you're ready to explore. Let's begin by understanding what bond enthalpy is. It's a measure of the energy required to break a specific bond in a molecule. In our case, we're looking at the Cl-Cl bond. Now, why is bond enthalpy a positive number? That's because breaking a bond demands energy from the surroundings, making it an endothermic process. We use the letter D, followed by the bond's formula to represent bond enthalpies like D, Cl, Cl, for the Cl2 bond. Moving on to diatomic molecules, calculating bond enthalpies is relatively straightforward. It's just the enthalpy of the reaction. However, when we deal with polyatomic molecules, things get more interesting. We usually resort to average bond enthalpies, and here's why. Good day, students. As we delve deeper, it's important to recognize the broader implications of bond enthalpies. They're intimately tied to the energy changes that occur during chemical reactions. By knowing the bond enthalpies of the reactants and products, we can predict whether a reaction is exothermic or endothermic. This helps us understand the feasibility of a reaction and whether it'll release or absorb energy. Now, during a chemical reaction, existing bonds are broken, and new bonds are formed. The energy required to break bonds is balanced by the energy released when new bonds are formed. This balance plays a crucial role in determining the overall energy change of the reaction. As we delve deep, let's sum up our journey today. Remember that bond enthalpy is the energy needed to break a bond within a molecule. The D symbol followed by the bond formula signifies bond enthalpies. While diatomic molecules have straightforward bond enthalpy calculations, polyatomic molecules rely on average bond enthalpies. These values are vital in predicting the energy changes during reactions and determining whether a reaction is energetically favorable or not. With this knowledge, we can explore the intricate world of chemical reactions with a deeper understanding. Null. Before we wrap up, let's make an exciting connection between bond enthalpies and the energy landscape of reactions. Bond enthalpies are intimately tied to the activation energy required to initiate a reaction. As bonds break and form, the reaction goes through a transition state. This state represents the highest energy point in the reaction pathway. By visualizing energy profiles, we can understand how bonds are broken, new bonds are formed, and the energy changes that occur throughout the reaction. It's like exploring the ups and downs of a roller coaster ride through chemistry. Welcome, students. Today, we're delving into the fascinating world of enthalpy and its correlation with chemical bonds. Enthalpy is a concept that helps us understand the energy changes that occur during chemical reactions. Let's focus on methane, and its CH bonds. In methane, there are 4 equivalent CH bonds. The enthalpy of a reaction involving these bonds is 4 times the enthalpy required to break a single CH bond. This leads us to the average CH bond enthalpy in methane, which is calculated as D1C He2 equals 1660 quarters kilojoule per mole. resulting in 415 kilojoules per mole. However, it's important to note that the specific bond enthalpy for a pair of atoms, like CH, can vary based on the molecules containing those atoms. Despite this variation, the differences between molecules are generally minor. When we explore CH bond enthalpies across various compounds, we find that the average bond enthalpy is around 413 kilojoules per mole, which is quite close to the calculated 415 kilojoules per mole value we determined from the dissociation of methane. This insight provides us with a deeper understanding of the energy dynamics within chemical reactions. Now, let's dive further into this intriguing topic. Welcome, student. Hello again, dear students. Today, we're delving deeper into the world of chemical bonds and the fascinating concept of bond enthalpy. Now, what is bond enthalpy, you ask? Well, it's a measure of how strong a chemical bond is. One important thing to remember is that bond enthalpy is always a positive value. Why, you might wonder? Because energy is needed to break chemical bonds. That's right. Breaking bonds requires an input of energy. On the flip side, when bonds are formed between gaseous atoms or molecular fragments, energy is released. So, the process of bond formation is actually exothermic. And here's an interesting connection. The stronger the bond, the higher its bond enthalpy. This means that bonds with higher bond enthalpies are harder to break because they hold their atoms together more tightly. So, as we continue, keep in mind that bond enthalpy is a key factor in understanding the energy changes that occur during chemical reactions. Let's move forward and explore more intriguing aspects of bond enthalpy. Hello again. Welcome back, students. In our journey through the fascinating realm of chemistry, we've encountered an intriguing concept related to chemical reactions and bond strengths. Let's dive right in. We've come across Table 5.4, which presents average bond enthalpies for various atom pairs. Remember, bond enthalpy is the energy required to break a specific bond between atoms. Now, here's an exciting tidbit. Molecules with strong chemical bonds are generally less likely to undergo chemical changes compared to those with weaker bonds. This brings us to an essential topic: multiple bonds. At times, atom pairs are held together not only by single bonds but also by double or even triple bonds. Take, for instance, the oxygen molecule, O2. Instead of a single bond, OO, it forms a double bond, OO, and breaking this bond requires a considerable amount of energy, around 495 kilojoules. This showcases the role of bond strength in chemical reactions. Let's proceed to our next topic for a deeper exploration. Welcome back, students. Hello again, dear students. Today's lesson takes us deeper into the realm of molecular structure and bond enthalpy. Let's dive into Table 5.4 and unravel the intriguing world of bond energies. Upon inspection, we find that the bond enthalpy for a double oxygen-oxygen bond, DO(O), is 495 kilojoules per mole. It's worth noting that this value isn't exactly twice the enthalpy of a single oxygen-oxygen bond, DO(O), which stands at 146 kilojoules per mole. This fascinating observation raises questions about the variations in bond enthalpy for different types of bonds. Curious minds, rejoice! We'll be delving into this topic with even greater detail in Chapter 8. So stay tuned for a comprehensive exploration of double and triple bond variations and the factors that influence their bond energies. But for now, let's continue our journey through the intricate world of molecular interactions. Hello again. Welcome back, students. In our exploration of energy production and chemical reactions, let's dive deeper into the crucial concept of energy input. When we're dealing with chemical reactions, we need to provide sufficient energy to break the bonds present in the reactant molecules. This energy input is necessary for the reaction to proceed. The result of breaking these bonds leads to an increase in the enthalpy of the system. Enthalpy is a measure of the total energy content of a system. In fact, the increase in enthalpy is directly related to the sum of bond enthalpies of the bonds that are broken. Think of it as the energy investment needed to kickstart a reaction. Now, let's move on to our next insight. Welcome back, students. In our exploration of energy production and chemical reactions, let's dive deeper into the crucial concept of energy input. When we're dealing with chemical reactions, we need to provide sufficient energy to break the bonds present in the reactant molecules. This energy input is necessary for the reaction to proceed. The result of breaking these bonds leads to an increase in the enthalpy of the system. Enthalpy is a measure of the total energy content of a system. In fact, the increase in enthalpy is directly related to the sum of bond enthalpies of the bonds that are broken. Think of it as the energy investment needed to kickstart a reaction. Now, let's move on to our next insight. Welcome back, Hello once again, young minds. Now that we've delved into some intriguing examples, let's take a closer look at what's happening on a molecular level during chemical reactions. In our second topic, we're going to explore the concept of bond formation and its connection to energy changes in a reaction. When a chemical reaction occurs, new bonds are formed in the products that weren't present in the reactants. This step is pivotal because it releases energy, which has a significant impact on the enthalpy of the entire system. Enthalpy, you might recall, refers to the total energy of a system. Now, here comes an interesting bit: the enthalpy of the reaction, increment Heinrich, can be estimated using a straightforward formula. It's the sum of the bond enthalpies of the bonds broken minus the sum of the bond enthalpies of the bonds formed. In simpler terms, the energy required to break bonds is subtracted from the energy released when new bonds are formed. This calculation gives us insight into the energy change within the reaction. And, as we venture deeper into our study, you'll realize the pivotal role this concept plays in understanding the dynamics of chemical transformations. Hello once again, young minds. Now that we've delved into some intriguing examples, let's take a closer look at what's happening on a molecular level during chemical reactions. In our second topic, we're going to explore the concept of bond formation and its connection to energy changes in a reaction. When a chemical reaction occurs, new bonds are formed in the products that weren't present in the reactants. This step is pivotal because it releases energy, which has a significant impact on the enthalpy of the entire system. Enthalpy, you might recall, refers to the total energy of a system. Now, here comes an interesting bit: the enthalpy of the reaction, increment Heinrich, can be estimated using a straightforward formula. It's the sum of the bond enthalpies of the bonds broken minus the sum of the bond enthalpies of the bonds formed. In simpler terms, the energy required to break bonds is subtracted from the energy released when new bonds are formed. This calculation gives us insight into the energy change within the reaction. And, as we venture deeper into our study, you'll realize the pivotal role this concept plays in understanding the dynamics of chemical transformations. Hello once again. Alright, my curious minds, let's apply our newfound knowledge to a real chemical reaction, the reaction between methane and chlorine. In this gas phase reaction, methane and chlorine combine to give us chloromethane and hydrogen chloride. The equation is CH plus Cl, right pointing arrow, CHCl plus hydrogen chloride. We're eager to find out the delta H for this reaction, aren't we? To do that, we'll delve into bond energies: the energy required to break a bond and the energy released when a bond forms. So, let's roll up our sleeves and calculate the enthalpy change for this intriguing reaction. Alright, my